The world's most advanced AI can pass the bar exam and write working code, then fail to count the R's in strawberry. I'm Kuro, and no, it's not being lazy. It genuinely can't see what you think it sees. That same blind spot is quietly making it worse at math and pricier in some languages than others. Let's find out why. Most people assume Kuro reads text one letter at a time, like we do. He doesn't. Kuro never sees a single letter at all. What he actually reads are chunks, and where those cuts land is about to get weird. Take the word tokenization itself. Kuro doesn't see 12 letters. He sees two chunks, tokenization. Those chunks are called tokens. But why cut the word exactly there and not somewhere else? So why not just feed Kuro one letter at a time? Simplest possible option. Because sequence length explodes. A short essay turns into thousands of characters. And processing cost grows with sequence length. Longer input, slower and pricier every time. Character level was tried early on. It didn't scale. So surely the fix is just swinging to the opposite extreme? Fine, swing the other way. Feed Kuro whole words instead. Problem. English alone has hundreds of thousands of word forms, and that's before typos. Run, runs, running, run. 4 separate slots for one idea. And any brand new word Kuro's never seen, there's simply no slot for it. So what's actually left to try? Characters are too small, whole words are too many. What would you try instead? Take a guess before I tell you. Comment it below. Got your guess in? Good. The real trick isn't as clever as you're picturing. It starts from individual characters, then merges the pairs that show up together most often. Repeat that merging step tens of thousands of times. This algorithm has a name, Byte Pair Encoding or BPE, and the mechanism behind it is stranger than it sounds. Here's the mechanism in real terms. Start with raw text as individual characters. Count which adjacent pair of symbols shows up most often across the training data. Merge just that one pair into a new single token. Repeat this exact process. Count, merge tens of thousands of times and watch two totally different words start sharing pieces. Take the classic textbook example, lowest and lowest in the training data. L and O appear together constantly, so they merge into low. Low and DW merge next into low, now a single reusable token. Low plus S becomes lower. Low plus S becomes lowest. Neither word needed its own dedicated slot. Multiply that trick across a whole language and see how large the vocabulary gets. This isn't theoretical. Every major model ships with a BPE vocabulary this size. GPT-4's tokenizer, Ekelo Varnasan के base, holds a bit over 100,000 tokens. Llama 3's tokenizer holds about 28,000. GPT-4o and O1 moved to a newer one, O200 base nearly 200,000 strong. Bigger has to be better, right? Bigger vocabulary, more tokens known by name. Purely a good thing. Or is there a catch? Hold that thought. We'll get to the catch soon. Guess it in the comments meanwhile. Now the actual answer to the strawberry problem. A token is atomic to the model, just one ID number like a barcode. The model never reopens that barcode to look at the letters spelling it. It can't count the R's in a token it never saw spelled out in the first place. Let's actually watch it happen. Watch what actually happens to the word strawberry. It doesn't arrive as 10 letters. It arrives as 2 opaque tokens, straw and berry. Kuro is being asked to count letters inside barcodes he can't scan open. That's the whole trick. Not a dumb AI, a text format it was never given. And letters aren't even where this gets worse. This is that quietly worse at math problem I teased back at the start, and it comes from the exact same root cause. Digits don't split consistently. 3880 might be one single token. 1234s might split into 23s and 4s, an arbitrary, inconsistent cut. Add two numbers chopped at different points and simple carrying can quietly go wrong, and numbers aren't even the priciest casualty here. Here's that pressure in some languages problem from the start. Vocabularies get built mostly from English, heavy training data. English needs roughly 1.16 tokens per word on average. Hindi needs almost double that, closer to 1.9 tokens per word. Same sentence, same meaning. More tokens burned, more money spent, less context window left. So what would you actually do about it? If you were building a global product, would you train a separate tokenizer per language? Or fix it another way entirely? Genuinely curious. Comment your take. People mix up tokenization with embeddings constantly. They are not the same step. Tokenization is a fixed, dumb lookup, text in, a list of ID numbers out. Embedding is a whole separate learned step. It turns each ID into a meaning carrying vector. Tokenization happens before the model even starts thinking. Embedding is the model's first real thought, and both are running in code you probably called without knowing it. This all runs in real name libraries, not research prototypes. OpenAI's Tick Token library is what actually implements SLA's Rule 100K base and O200 base. Meta's Llama models use a byte-level BPE tokenizer built on Google's SentencePiece framework. BERT from Google used a close cousin called WordPiece. Same spirit, slightly different merge rule. All chasing the same bigger vocabulary trend, but is bigger actually free? So back to that catch from a minute ago. A bigger vocabulary costs something too. More known tokens means shorter sequences for the same text. That part's genuinely good. But every extra vocabulary entry adds a row to a giant lookup table the model must hold in memory. Go too large and that table itself becomes the bottleneck, not the sequence length. So is a fixed vocabulary just something we are stuck with? Turns out, no. A few labs are trying to kill the fixed vocabulary altogether. Byte Latent Transformer, or BLT, drops the fixed vocabulary entirely. It groups raw bytes into patches on the fly, based on how predictable they are. Early results show it spelling correctly on exactly the tasks that trip up token-based models. It's still experimental research, not what's running in production today. But cracks like this have a way of spreading, so how long does BPE really have? If Tokenizer-free models mature, do you think BPE disappears within 5 years? Or does it stick around the way JPEG still has? Decades later, your call. Comment it. Let's wrap the whole trip back up fast. Text gets cut into tokens by repeatedly merging the most common adjacent pairs. Those tokens are atomic, barcodes the model can't reopen to spell out. That's the entire strawberry mystery solved. That's tokenization, the quiet first step behind everything an AI model ever reads. Next time, how AI actually sees images and video in a text-shaped brain. Tell Kuro in the comments how many hours did you think were in strawberry. Subscribe while you're at it.